So at the very end of our last lecture, we talked about the Pythagorean identities. So the Pythagorean identities, there were 3 of them. Let's review what they are. So the first one was just our Pythagorean theorem. If you remember, we took it from the right triangle, from the triangle in the circle. Right? Let's go back. If you notice, we took it from this right triangle here. We said the bottom of our triangle is x, the vertical side is y, and the hypotenuse is 1. Okay, so we said, okay, the relationship in the circle is that x squared plus y squared is equal to 1. So we know that the sine of theta is y and the cosine of theta is x. So we can also say that cosine squared theta plus sine squared theta equals 1. And just that also means that sine squared theta plus cosine squared theta equals 1 because of the commutative property. The order of addition doesn't matter. So we came up with that, sine squared theta plus cosine squared theta equals 1. And then we said, okay, well, we could get the other 2 Pythagorean identities by dividing everything by sine squared or dividing everything by cosine squared theta. We also derived them by just taking the Pythagorean theorem itself. O squared plus a squared equals h squared. And we divided everything by h squared, divided everything by o squared, and divided everything by a squared. And that's how we got our 3 Pythagorean identities. And then something else that we said was to just be watchful that all 3 of these Pythagorean identities can actually be written in 3 different ways, because we could solve for each of the 2 trig functions that you see in the Pythagorean identity. And you could also solve for 1. You can make it equal to 1. So this one is already equal to 1. This one, when we make it equal to 1, it's 1 equals cosine squared theta minus cotangent squared theta. And this one, when we make it equal to 1, it's secant squared theta minus tangent squared theta. So we have these 3 different ways of writing each of the 3 Pythagorean identities. Some things I want you to notice is that sine and cosine are paired. Cosecant and cotangent are paired, so we have the cos paired. And then we have secant squared and tangent squared paired. All of these trig functions in the Pythagorean identity have squares. So if you see a trig function that is not squared, you cannot use a Pythagorean identity. Okay. Also, something else to notice, if secant squared theta minus tangent squared theta is equal to 1, then remember, if you switch what's on each side of the minus sign, so you make it tangent squared theta minus secant squared theta instead, okay, we switch the order of what's on the minus sign, then that's equal to -1, right? 3 minus 2 is 1, but 2 minus 3 is -1. So just keep that in mind too. And why is this important? Because when we do these Pythagorean identities, so let's write them down here one more time. We have sine squared theta plus cosine squared theta equals 1. Then we have 1 plus cotangent squared theta is equal to cosecant squared theta. And then we have tangent squared theta plus 1 is equal to secant squared theta. We also have a couple of other things that I want you to remember, okay? Remember your reciprocal functions, right? So cosecant squared theta is 1 over sine squared theta. Secant squared theta is 1 over cosine squared theta. And sorry, blanked out for a second. Cotangent squared theta is 1 over tangent squared theta. These are our reciprocal identities, right? And then we also have our quotient identities. And we know these as well, actually. We did not refer to them as quotient identities, but our quotient identities are that the tangent of theta is equal to the sine of theta over the cosine of theta, and therefore the cotangent of theta is equal to cosine theta over sine theta. Okay, so why is this important? Because just like with logarithms and just like with exponential expressions, we could take a trigonometric expression and we can simplify it. Okay, so let's take a bunch of examples. And this is the type of thing where sometimes you just have to try. You just have to do stuff. Okay, so let's take an example and you'll see what I mean. Okay. We'll start doing examples in a different color so that you know that we're doing examples. And you kind of learn by doing. There's no other way of learning this. You learn by doing. So we have 1 minus cosine squared theta times the cosecant of theta. And we want to see, can we write this in simpler form? Can we write it as one trigonometric function? Okay, because this kind of it looks complicated. So let's see if we can simplify it. And what we're doing is we're really looking for one of these identities. And we're saying, can we use these identities to help us simplify this expression? And we actually can. So we're going to be looking for all kinds of things. But again, look for the identities first and say, can I rewrite any of this? And we actually can rewrite some of it, right? We see 1 minus cosine squared theta. So the first thing that you can look for is, do you have any trig functions squared? Because if you have a trig function squared, the next thing that you're going to say to yourself is, okay, is it a Pythagorean identity? And 1 minus cosine squared theta is a Pythagorean identity, okay? Sine squared theta is equal to 1 minus cosine squared theta. So this is why you have to be familiar with this idea that every one of those Pythagorean identities can be written in a different way. So sine squared theta is equal to 1 minus cosine squared theta. So we can do a replacement, okay? We could take this 1 minus cosine squared theta and we can say, hey, that's equal to sine squared theta. So let's rewrite this as sine squared theta times cosecant of theta. Now notice this cosecant is not a Pythagorean identity. Every one of the Pythagorean identities has a trig function squared, okay? As soon as you see trig function squared, you're going to look for another trig function squared, or you're going to look for a 1. A 1 indicates that you have a Pythagorean identity, okay? When you have a plus or a minus, the idea is let's try and get rid of plus or minus. You never want to take something that doesn't have addition and subtraction and then put it in, okay? You want to try and avoid that as much as possible. So now we're going to look for anything else. So we have sine squared. We can't really do anything with that. So we would not want, if we started off with this, you would not want to turn it into this, where you change the sine squared into a 1 minus cosine squared. Don't do that, okay? Okay, so now what? Well, we have cosecant of theta, and cosecant of theta can be rewritten. I put 1, I'm going to take out the squares here. We don't want the squares. There's no reason for the squares. This is all true. There's just no reason to have the squares in there. So I'm going to take out the squares from these reciprocal identities. It's not that what I wrote is incorrect. It's not incorrect, okay? It's that what I wrote is unnecessary. The reciprocal identities are actually without the squares because it's true with or without, so we may as well write it without. So we have cosecant of theta is equal to sine of theta. we have secant of theta is equal to cosine 1 over cosine of theta, and we have cotangent of theta is equal to 1 over tangent of theta. Notice I always put in theta. Always. Do not leave out theta. Do not write COT equals 1 over TAN. Okay? COT without the theta means absolutely nothing. It is just a cut. Okay? TAN without the theta, that's just a color tan. That means absolutely nothing mathematically. You must have the theta. So don't be lazy about it. I will take off points if you leave that out, because then what you're doing is you're saying you do not understand that this is a function of something. You have to take cosecant of something, okay? So now what we could do is we could say, okay, well, cosecant of theta could be written in terms of sine. And you can either say that this is sine squared theta over sine theta, or if you don't feel comfortable doing that right away, you can write it as two separate fractions. I'm rewriting the same thing. I'm just doing it in blue. Okay, so you can skip this step. You can just say, okay, well, this is sine squared theta over sine of theta. And then what happens? Well, we have two sine of thetas in the top and we have one in the bottom. So one of them will cancel. So what are we left with? Sine of theta. And that's our final answer, right? We can't get any simpler than sine of theta. Okay, so this is one way that we can simplify a trigonometric expression. So we're looking for these different identities and we're saying, what can we do? And sometimes you're going to try it, you're going to have no place to go, okay? And if you have no place to go, then go back and try something different, okay? And you're going to see that even here when I do it, you might even see something like that, okay? Okay, let's take another example. And we can actually fit it right next to this one. Let's say that we have cosine squared x plus cosine squared x times tangent squared x. Okay. Now sometimes there's more than one way to do things. So we're going to do this using two different methods. Okay, I'm going to show you two different ways to do it. And which way you choose is up to you. As long as you don't break any rules, you can do whatever you want. Okay, so as long as you don't do something that is mathematically incorrect, okay, you can do whatever you want. So what can we do first here? Well, I see trig functions that are being squared, which tells me I am likely to have a Pythagorean identity, especially since I see a plus sign, okay? As soon as we see a trig function squared and a plus sign, you want to think Pythagorean identity. However, this does not look like any of our Pythagorean identities. So you can either say, okay, I might have one, but I don't have one yet. Or you can say to yourself, what might I do to get one? Okay, so if you're trying to think, what might I do to get one? Then you might say, okay, well, how can I turn this into a 1? I can pull out a cosine squared. So factoring should always be on your mind, okay? Both of these terms have a cosine squared inside of it, so we can pull out a cosine squared. It's a common term. Notice here I'm using x. You can use whatever you want, okay? I just wouldn't use like I or E, okay? For obvious reasons, those are actual, they have actual values. But if it's an x or a theta, we've seen both of them have been used. So we could pull out a cosine squared theta. And what we're doing is we're dividing each term by cosine squared theta. So what we wind up with is 1 plus tangent squared. And we're using x, so use what is given to you in the problem, okay? So if this is x, use x. If this is theta, use theta, okay? Okay, so now what? Well, now we see a Pythagorean identity because 1 plus tangent squared x is secant squared x. So we can do a replacement. And what can we do from here? I will do this in multiple steps, but you could actually skip straight to the last step if you wanted to, and we'll explain that in a second, okay? So we could actually say, okay, secant squared is the same thing as 1 over cosine squared x. So we could rewrite this, and again, you do not have to do this separately. You can automatically say this is cosine squared over cosine squared. I'm doing it separately for anybody who is not comfortable multiplying the fractions in one step, okay? Because remember, this is like cosine squared x over 1, okay? So we're just multiplying straight across. And this cancels out and it just becomes 1. Okay, well, what does this mean? We have cosine squared x times secant squared x. Well, cosine and secant have a relationship. They are reciprocals. And what happens when you multiply something by its reciprocal? You get 1. This is the multiplicative property. This is the identity property of multiplication. When you multiply something by itself, when you multiply something by its inverse, you get 1. Okay, multiplying something by its inverse, you get 1. B times 1 over b is 1. Okay, 3 times 1 over 3 is 1. So it turns out that whenever you're multiplying a trig function by its inverse, you get 1. So we can actually even add that to our list here. I will add it in a different color because these don't have specific names, okay? So if we do cosine x times secant x, this is equal to 1. If we do sine x times cosecant x, that's equal to 1. And if we do tangent x times cotangent x, that's equal to 1. Okay, and this is the identity property of multiplication. Okay, it's their multiplicative identities. This is really, we would call it the inverse property. The identity property would be, what do you multiply it by itself? What do you multiply it by in order to get itself back? So you would multiply by 1. Okay, this is not just for trig functions. This is also for every number, okay? So it's the inverse property of multiplication. I kept calling it the identity property. The identity property is the other way around. It would be saying that cosine x times 1 is cosine x. Okay, how do you get itself back? Identity. Okay, this is one method. There is another method for this. If you did not see that you could pull out a cosine squared, okay? Oh, let me go back to that inverse property one more time. What we're saying by the inverse property is we're saying we actually could have went straight from here to here. We could have skipped over both of these steps and said, This is the inverse property of multiplication. So these are inverses of each other, okay? They're reciprocals of each other. So therefore, I can just say when we multiply them, we get 1. So you could have skipped over both of these steps as opposed to just this step here, okay? Here, you couldn't do that. You couldn't skip over these steps because this was not a cosecant squared. Okay, so they're reciprocals, but they weren't direct reciprocals because one was squared and one was not. Okay. Okay, let's go back to figuring out what that second method was. So let's say that you didn't see that both of these had a cosine squared in common. What you could have done is you could have taken the tangent squared and you could have said, okay, well, I could write tangent squared in terms of cosine squared. So let's do that. This is another method. And you get cosine squared x plus cosine squared x times sine squared x over cosine squared x. So you're using that identity property. And again, we could cancel right here. I'm not gonna write this as one thing. We could cancel the cosine squared x right away. And that gives us cosine squared x plus sine squared x. And what is cosine squared x plus sine squared x? It's 1. Okay, this is another method. For the second example. And that's going to happen a lot where there's actually not one way to do something. There are multiple ways to do the same problem. And it depends on what you see, okay? What you look for. So again, sometimes this will take you a little bit longer to do, okay? Sometimes you'll be able to do it very quickly, okay? Okay, let's take another example. We're just going to do a bunch and then we're going to switch gears just a little bit. The only thing that I ask here is when you do this like on an exam or any sort of assignment, that you organize your work well. So it's easy to see what your different steps are. So some people just kind of write it all together. If you notice, it's easy to see that I did this first, then this came, then this, and then this. So just try and be a little bit neat about it so it's easy to follow your work. Okay, and that would be true about anything in math. So if we take the next one, let's take something that maybe is a little bit, requires a little bit more work. Okay, so here we use x again. Doesn't matter, not really a preference. We have cosecant of x minus cosecant of x times cotangent of x. And this might be another case where you're kind of sitting there and saying, okay, I don't see any square functions, so there are no Pythagorean identities yet, okay? There is a minus sign, which kind of indicates that maybe we might be able to do a Pythagorean identity, okay? So what do? Okay? So there are different options here. We see a cosecant of x. We could pull out a cosecant of x. Okay, now if we pull out a cosecant of x and we move it out to the front, we get 1 minus cotangent of x left over. And that's still not a Pythagorean identity. So you might look at it from a different perspective. Okay, you might do it differently. So because we don't see a Pythagorean identity, let's take something that's kind of a fail-safe method, something that you can always do if you get stuck, okay? If you get stuck and you're not sure, okay, one thing that you can do is you can always convert everything so that it's in terms of sine and cosine. This is a good thing to do when you're completely stuck. You see it, you're like, okay, can't do anything. Take cosecant of x, convert it to something out of sine and cosine. Everything can be converted into something in terms of sine and cosine. Cosecant is 1 over sine. Secant is 1 over cosine, tangent is sine over cosine, and cotangent is cosine over sine. So everything could be written in terms of sine and cosine. So do that, okay? That's a method that you could use. We can, by the way, we absolutely can factor out cosecant of x. I'm not going to use every method that we have. Ultimately, though, okay, ultimately, we are going to want to convert things into sine and cosine here. So that's why I'm going to start by doing it here, okay? So cosecant of x is 1 over sine x. Then we have cosecant of x again. So we have minus 1 over sine x. And then cotangent of x is cosine x over sine x. So I'm just going to rewrite this. We have 1 over sine x minus cosine x over sine squared x. Okay, well, we have two fractions, so now we're back again. And it's kind of like, okay, well, what do we do now? I converted everything into sine and cosine, combined this, and now I'm still stuck, okay? Well, your next step would be, can we combine fractions? Can we get rid of the addition and subtraction? Ideally, we'd like to do that, okay? So how do we add and subtract fractions? You need a common denominator. So we look and we say, what does the other denominator have that this one doesn't? Well, the other denominator has 2 signs. This one only has 1. So that tells us we need another one. So we're going to multiply it by sine over sine. Okay. So what did we do here? Again, these are fail-safe things to do. Convert everything into sine and cosine. That's a good first step, okay? And then what do we do next? We combined fractions. And what you're going to see here is that by combining the fractions, we actually accomplish something. So this gives us sine x minus cosine x over sine squared x. Okay. So our next question is there anything else that we could do? Okay, this is a great example of a problem where you get to this point and you look at it and you say, I converted everything into sine and cosine. I combine the fractions. Sine x minus cosine x isn't equal to anything at all. So this is it. We're done. How do you know when to say that you're done? So first of all, I wrote this problem incorrectly, which is why we got stuck here. When I looked at my paper, I thought it's cosecant, but it's actually cosine. So we're going to redo it with cosine. But I'm not going to go back and delete this from the video because I think it's really important for you to see that sometimes you just have to say, I can't do anything else. You're saying, I did everything that I could do. There are no Pythagorean identities here, okay? You don't want to take a sine squared and convert that back into a cosine squared. You do not want to, into a 1 minus cosine squared. And the reason for that is you don't want to take something that does not have a plus or a minus and give it a plus or a minus, okay? Sine x minus cosine x There's nothing that you could do with that. There's nothing that can be canceled here. Okay, remember the sine x minus cosine x has an invisible parentheses around it. So you cannot cancel. Okay, so you're done. And sometimes you just have to accept that you're done. You might go back and you might try to factor out a cosecant of x. But if you factor out a cosecant of x, you're going to run into the same problem. So let's do this problem again, but do it with the correct values. Okay, and I will make you a promise that I won't give you a problem like this on a test. Okay, the problems I give you will actually simplify to something. So the actual problem was cosecant of x minus cosine of x cotangent x. Okay, so we would approach this in exactly the same way. It's just that this time we'll actually make some progress when we do this. So we get 1 over sine x. Cosine x is already in terms of cosine. And then this becomes cosine x over sine x. And here you're going to see that there actually is progress that's made. This becomes 1 over sine x minus cosine squared x over sine x. Okay, so again, we converted everything to something in terms of sine and cosine. And in this problem, you didn't even have the choice of factoring something out. There's nothing that can be factored out here at this point. Okay, you could factor out a 1 over sine x now if you wanted to. There's not really much point in doing that, but you absolutely can factor that out. Okay. What does this give us? We can combine fractions, but we already have a common denominator. So we don't have to create a common denominator like we did up here. So we get 1 minus cosine squared x over sine x, which gives us sine squared x over sine x. And just like one of the previous problems, one of the signs can cancel, which leaves us with just sine x. Okay, let's review what we did. So in our first step, you get stuck, convert everything into sine x and cosine x. That could always be a first step. Sometimes it's easier not to do that. So for example, here, it might have been easier not to do that if you recognize that when you pulled out the cosine squared x, you would wind up with a Pythagorean identity. You should always look for those Pythagorean identities. They can make your life simpler. Okay, but this is a fail-safe method. It will always work. Okay, then we combined our fractions. We substituted a Pythagorean identity. And then we just simplified. Okay, so you're kind of just going and sometimes you're just saying, okay, what's something I could try? Sometimes you're not looking for anything in particular. If you're stuck, you might not see it. So you're saying, okay, what do I do? This is an option. I see fractions, this is an option. Then I see Pythagorean identity, this is an option. So you're going one step at a time and you're saying, what's something that I could do that's allowed? Okay, let's do a couple of more. Well, here's another example where you're kind of looking at it and you're like, okay, I have no idea what to do. What do we do here? Okay. And everything is already in terms of sine and cosine. Okay. So what do we do? Now, some of you may see cosine theta over sine theta and say, hey, that's cotangent of theta. Maybe I should change it to cotangent of theta. Hey, you want to change it to cotangent of theta? Try it. See if it works. See if it goes anywhere. Okay. And it might. I don't know. Looking at this right now, I don't see a place for it to go. Okay. But that doesn't mean that it can't. Okay. The next thing that you're going to say is you're going to say, hey, these are fractions. Let's try and combine the fractions. And let us try and combine the fractions. Okay. That would be the next thing that I would think of to do. And that would mean we have to multiply. We have to find a common denominator. So we're going to look at this denominator and say, what does the other denominator have that this one is missing? The other denominator has a sine of theta. So let's multiply by sine of theta over sine of theta. Now we're going to do the same thing with the other fraction. We're going to say, what does the other denominator have that this one is missing? Well, the other denominator has a 1 plus cosine theta. So let's multiply by 1 plus cosine theta over 1 plus cosine theta. So again, we don't really know where this is going to take us. Some of you are going to see and you're going to say, oh yeah, that looks like it's going to do something for us. But others are going to look at it and be like, I have no idea what I'm going to see in the end. Okay. So you're just working through the combining fractions now. So sine of theta times sine of theta gives us sine squared theta in this fraction for the numerator. We know that we try and avoid multiplying the bottom until you feel like, hey, there's nothing else I could do. But multiplying the tops, always a good idea. So we would distribute this cosine. It's always a good idea to multiply the tops. Again, if you see something where you're saying, hey, this doesn't help to multiply, I should leave it factored, leave it factored. But the problem with leaving it factored is that then you can't combine these. You can't add them, right? So that's why we would probably multiply it out. And what you'll find is that when you leave it factored, you're going to feel stuck. So that would be your next step, okay? So what we did is we're combining fractions first. Okay, so we found a common denominator. And then if we keep going, again, we're going to leave this just as sine theta over 1 plus cosine theta. And our next step would be to combine, right? Put it all as one fraction. Now here, this is where you kind of have to be a little creative. You have to look ahead and say, okay, I have trig functions that are being squared, and I have 2 of them. So I have a sine squared plus a cosine squared. Sine squared plus cosine squared is a Pythagorean identity. It's 1. So we could replace the sine squared with cosine squared, the sine squared plus cosine squared, with 1. Notice I always put in, I don't always say theta, but I always write theta. And what do we see here? We see a factor that we can cancel. 1 plus cosine theta cancels with 1 plus cosine theta. And we are left with 1 over sine theta. Now, do not leave it like this, okay? Don't leave it like this. If you can write it as one trig function, then you should. Write as simply as possible. So you want to turn this into the reciprocal function. So 1 over sine theta is cosecant. Cosecant of theta is your answer. Now, this is not to say that this is the only way to do this. I believe it's the most efficient way, but it is possible that if you wrote this as cotangent of theta, it is possible. I'm not going to say it's impossible. It is possible that you might find a different way of simplifying this down to cosecant of theta. Okay. Okay, let's take one more where it just looks like this. Let's take 1 over 1 plus sine of theta plus 1 over 1 minus sine of theta. Okay, again, this looks complicated. It looks like something we really don't want to do. Okay, I understand that. But we've already know how to approach this. So everything is in terms of sine. There's no other trig function there. So we don't have to start with that converting to sine and cosine. But we have fractions. And once again, we know that when we have fractions, that's a good first step to start combining our fractions. So in order to combine our fractions, we need a common denominator. This has a 1 plus sine of theta, but this one has a 1 minus sine of theta. Now remember, these are groups. They are grouped together. So we have to multiply by the whole group, okay? So that means that for a common denominator, we're going to multiply this fraction by 1 minus sine theta over 1 minus sine theta. And same thing on the other side. We have to multiply by 1 plus sine theta over 1 plus sine theta. Okay, so what do we get? Well, 1 minus sine theta times 1 is just 1 minus sine theta. And again, it might be that at a certain point, you want to multiply those out. And some of you are going to see right away that if we do this, it might be helpful, okay? But I want to do it in the beginning. I would let it be because you never know when you can cancel a factor, okay? You just don't know. Be careful, don't start canceling now, right? Because then you're undoing this multiplication by 1 minus sine theta over 1 minus sine theta. Once you find your common denominator, you don't start canceling until after you combined the fractions. Then you can consider canceling, but you have to combine the fractions first. Otherwise, you're undoing the work that you did. Now we have 1 plus sine theta, again, over 1 minus sine theta, 1 plus sine theta. Now we're just combining, so numerators, and you can, when you combine at this point, you can just add it. I'm going to do it in 2 steps, okay? So we're going to write it as one numerator, and then we're going to add. Okay. And some of you are going to see that we have a negative sine theta and a positive sine theta on top. So those go away. And 1 plus 1 is 2. And you can combine certain steps. Please be careful though on your test. Some of you are combining so many steps that there is no way for me to see how you get from one step to the next. So like for example, some of you are going straight from here to our next step. Okay, you're skipping 2 steps. Never skip 2 steps because then I have no idea where it came from. Okay, so what I mean by to the next step, at this point you have to say, okay, well, can I simplify this any further? Because this still looks really complicated. Okay, so at this point you might say, well, let me multiply the denominators. Let's actually multiply these factors and see what happens. And a lot of you are going to see right away that this is a difference of squares. If you don't see it, then you're just distributing everything in the first set of parentheses to everything in the second set of parentheses. And you will see that what you get here is 2 over 1 minus sine squared theta. So some of you on your tests are going straight from here all the way down to here, and I have no idea. I mean, when I look at your work, I'm going to have no idea how you got there, okay? Which is going to tell me that you have no idea how you got there. So remember, mathematics is about communication. If you are not communicating your method, then the assumption is you don't understand your method, okay? Whenever you do mathematics, it has to be everything that we do in this world. We repeat. When we do studies, they get repeated. A lot of you are watching the news about the coronavirus. They don't do one clinical trial to see if a medication is a treatment or if a vaccine works. They do 100 clinical trials to see if it works because they want to repeat the work and make sure it's correct. The same thing is true with math. You want to be able to reproduce the work. If you can't reproduce it, because it doesn't make sense how you get from step 2 to step 5, okay, because you don't have anything in between, then it's not worth anything to anybody. So that's why you have to include steps. It is okay to go from here to here. It is okay to skip a single step. It is not okay to combine numerators and do denominators and go straight to here. Okay, some of you are doing that. Please do not do that. If you're finding common denominators, even here, don't skip this step here. Show us what your common denominators are. Show us what you're multiplying by. Because a lot of people, it's not going to be clear when you get to this step. So if you're not sure, and if you were looking at this and you were saying, hey, I don't think I could reproduce this. And I certainly don't think that, you know, somebody in my family is going to understand what happened, then you need to write it. You're always better off writing more than less. Okay, that's my lecture to you. So from here, you want to keep going. You want to say, hey, I have a trig function squared. Pythagorean identity. This is 2 over the cosine squared theta. And cosine squared theta is the same when you have it in the denominator, right? That's the same thing as secant squared theta. 1 over cosine is secant. So 1 over cosine squared is secant squared. So what did we do here? We found a common denominator first. What does the other denominator have that this one doesn't? I'm going to put this in greens just so that you can distinguish between it. Okay. I want you to distinguish clearly between the annotations and the mathematics. So we found a common denominator here. The next thing that we did is we combined the fractions. We combined like terms in the numerator. So that's when we were able to cancel out the signs because one was positive and one was negative. And 1 plus 1 is 2. Then what we did is we said, okay, well, this still isn't simple enough. So it's not simple enough. Let's try multiplying the factors in the denominator. And that's when we saw the Pythagorean identity. Okay, and we substituted the reciprocal function finally. So we essentially combined fractions and went as far as we possibly could, okay? And now that we have one trig function, there's obviously nothing else that we could do. Okay, so where can we take this from here? We can do something called verifying an identity, okay? So I'm going to give you an example of what that means. And then instead of solving it right away, what we're going to do is we're going to talk about how we would solve it. And then we're going to go through and do a bunch of different examples where we're verifying identities. Okay, some of them really simple, some of them a little bit more complex. Okay, so verifying an identity. So what do we mean by this? What we mean is that we have something on one side we have a trigonometric expression on one side. So for example, cosecant squared of theta over cotangent theta. And we want to show that it's equal to a trigonometric expression on the other side. That's what we mean by verifying an identity. Okay, or vice versa. We can work with the left and then the right, showing that a trig expression on the left equals the trig expression on the right. Okay, so that's what we mean by verifying the identity. Now, clearly we could essentially just simplify both sides, do what we've been doing, except now we have two sides to do it with, okay? Or we could just say, well, we're going to simplify one side as much as we can until it looks like the other side, until it's the same as the other side. So maybe we don't have to go all the way to a single trig function. Maybe what we could do is start simplifying this until it looks exactly like cosecant theta, secant theta, and then we can stop. We don't have to simplify both sides all the way down. We just have to simplify each one until they look like each other, until they're equal. Okay, so hopefully that makes sense, that we don't have to simplify completely. We just have to simplify to a point where the left side equals the right side. Okay, so how do we do this? So there are some guidelines that we follow. And we talked about a lot of them already. So this is very important. Work with one side of the equation at a time. What does this mean? It means don't do things like cross multiplying. I don't like the word cross multiply. But don't multiply both sides of the equation by 2. Don't multiply both sides of the equation by 1 plus cosine theta. Okay? Never do something to both sides simultaneously. Okay? The reason for that is sometimes you wind up getting rid of a trig function and it just disappears, and it wasn't supposed to disappear. Okay? So you just want to be careful about that. When we do equations, you'll see great examples of that. So don't always, you're simplifying one side of the equation. You can choose to stop and start simplifying the other side of the equation, but you should never say, okay, I'm doing this to both the left and the right, okay? Because again, you don't want to cancel something out that shouldn't have canceled, okay? Second thing, you want to look for opportunities to do things to help you simplify. So what are we looking for? Factoring. Look for something that both terms, not both expressions, but both terms in a single expression. Look for something that they both have in common. So factor an expression. Look for opportunities to add fractions. So we saw both of these in the examples of simplifying expressions. Try squaring something. Or that's it. I'm going to take this out. I don't want you to get confused by squaring a binomial, and I'm afraid it'll confuse you. Okay. Look for Pythagorean identities. Or other identities. And there are others. We're not going to be concentrating on them, but there are others that you might be able to use. We're just not looking at them right now. Okay. Remember, that sine theta times cosecant theta equals 1. Cosine theta times secant theta equals 1. And cotangent theta, tangent theta equals 1. If all else fails, convert everything to sines and cosines. And this is important. Always try something. If you sit there and you stare at it, nothing will happen. You won't know what's going to work and what's not. Okay? So It's okay if it leads to a dead end. You can always try something else, and this tells you something. One of the things that we talked about at the very beginning of the semester is that wrong answers tell you just as much and sometimes more than right answers. But sitting and staring at the problem isn't going to help you solve it, right? So you always want to try something, anything, okay? And if you get stuck, you get stuck. You try something else, okay? So let's take this example here. Of cosecant squared theta over cotangent theta is equal to cosecant theta times secant theta. Okay, let's try this. Let's see what happens. Okay, now I'm going to put this in black so that you don't, I'm sorry, I pressed the wrong thing. I'm going to put it in black because I don't want you to confuse. I want you to see that it's an actual example. Okay. I'm rewriting exactly the same thing. And if you get stuck on one side, start simplifying the other side. All you have to do is get them to be the same, okay? You just have to get them to be the same. So it doesn't need to simplify completely. So let's figure this out. There are many different ways that you can do this, okay? So I'm going to show you one way, but there are multiple ways. So if you find a different way, but you wind up in the same place where left side equals right side, then you're okay. So you choose a side. You say, where do I start? You can start with whichever side you prefer. Sometimes it can be easier to start with the more complex side because you can do more with it. Okay, so for example, we have cosecant squared. Well, cosecant squared is a trig function squared. Do not, again, I will remind you, do not take cosecant squared and convert it to a Pythagorean identity, okay? Cosecant squared as a Pythagorean identity is equal to 1 plus cotangent squared. Now, you're going to see cotangent, but this is not going to help you necessarily. I would not put a plus or a minus in unless you see a plus and a minus on the other side, okay? But I would never add a plus or a minus if it's not there. So cosecant squared, what we can do is we can, some of you are going to start by, okay, what I would do is I would start by thinking about sines and cosines, okay? The thing is, and this is a good way of looking at this, I see a cosecant on the right. So because I see a cosecant on the right, the only thing I'm going to change in terms of sine and cosine is the cotangent. I'm not going to change anything other than the cotangent here, okay? Because I see a cosecant on the right, so I may as well leave it on the left. Okay, so because of that, I'm not changing everything. I'm trying to be efficient here, okay? And that's up to you. You can change everything or you can try and be efficient. I'm only working with the left side, okay? And I'm trying to make the left look like the right. So I am only going to change the cotangent because I see a cosecant on the right and I see it on the left. So this I'm going to turn into cosecant squared theta over, and cotangent is cosine over sine. I am leaving this side alone. Now what can we do here? We can multiply this by the reciprocal, right? We can multiply both the top and the bottom by the reciprocal. We get cosecant squared theta times sine theta over cosine theta. Okay, so I look at this. I'm going to bring this up here so that hopefully we can fit it all on one page. Okay, so notice I'm just carrying the left side. I'm carrying the right side down. Okay, this I'm just carrying down each time. And I'm going to continue to carry it down. So that's just the left side that we're just the right side that we're just leaving the same. So this is a case where I'm looking at where I'm going, and I'm trying to make where I'm going look the same. So I have cosecant squared theta times sine over cosine, but cosine is in the denominator, and I see a secant here. So I'm going to take this 1 over cosine, and I'm going to replace it with secant. This is not the only way to do this. Okay, this cosecant came from 1 over cosine. Okay, so I wrote sine. I meant secant. And actually, I'm going to put, sorry about that. Okay, so this secant came over the fact that there's a cosine in the denominator. We took it out of the denominator. That's why I messed up. I apologize for that. I took the cosine out of the denominator and made it into a secant. The sign stays there. Okay, but then there's something else here. Cosecant times sine is just 1. Okay, so I'm gonna do an extra step here. Okay, I'm gonna write this cosecant squared as cosecant times cosecant. Now cosecant times sine is 1. This is a reciprocal. This is equal to 1. They're reciprocals. So what do we get when we take that? We make it equal to 1. We get cosecant theta, secant theta is equal to cosecant theta, secant theta. And because we have that, we're done. We don't have to simplify even further. It is not necessary. Now, we didn't have to do it this way. We could have changed cosecant squared theta into 1 over sine squared theta. Okay, and then you would have had a sine of theta that canceled, and you would have been able to get the cosecant theta, secant theta just as quickly. Okay, that would have been another option. So let's actually go through that option. For this problem only. For the others, I'm only going to do it in one way. So we had cosecant squared theta over cotangent theta is equal to cosecant theta, secant theta. So this would have been another option. We could have said cosecant squared is 1 over sine squared. And cotangent is cosine over sine. Okay. Now what we could have done is we could have said, okay, let's multiply by sine over cosine. Right? That's going to cancel the bottom. And we're going to multiply by sine over cosine here. Now this sign cancels, and one of the signs down here cancels. So what are we left with? We are left with 1 over sine theta times 1 over cosine theta. And for each of these, we still equal cosecant theta, secant theta. Okay, these just carry down. Okay, now we have two options. We could take 1 over sine theta and convert it to cosecant, and 1 over cosine theta and convert it to secant. Or we could do it the other way. We could carry this down now. And replace cosecant with 1 over sine and secant with 1 over cosine, whichever you're more comfortable with. And in the end, you have your little check to say, okay, the left side is equal to the right side. Okay, so the arrows tell you which side is getting carried down. And notice, we simplified the left side and then we moved to the right side. Okay, let's take a different example. Let's do sine squared plus cosine squared over cosine squared times secant squared is equal to 1. Now this is an example of one that's very simple. Okay, and the reason why it's very simple is because we're looking for all of those things that we should be looking for, and we're going to see them right away. So for example, one of the first things that we look for is a Pythagorean identity, and we have one. So this turns into a 1. We also see reciprocal functions. And when we multiply reciprocal functions, we get a 1. And 1 over 1 is equal to 1. Okay, and this is a good example of where we would only ever simplify the left side, because the right side is in its simplest form. Okay, let's take another one. We'll do a few. And these are places where you can pause the video, try it yourself, but I will warn you that there will be times where when I do it, it looks totally different from what you do, okay? And you just have to look through the work. At any point, if you try these yourself and you did it in a different way and you want to check to see if what you did is correct, then just send me an email and say, this is how I did it. Did I do it correctly? And I will tell you, okay? But again, you have to show all of your work. So even here, if you notice off to the side, I put what I did so that you could see where I'm getting this 1 over 1 from. I'm not just writing it. I'm telling you where it's coming from, okay? Let's take secant squared theta minus 1 over secant squared theta is equal to sine squared theta. So this is an indication that this is really simple already. So this would be an indication that I'm only working with the left side, okay? There are two ways that we could do this. we could split up the fraction. I'm not going to do it this way because it's not as familiar to people. We could split up the fraction and say secant squared theta over secant squared theta minus 1 over secant squared theta. And what you wind up getting is 1 minus cosine squared theta. And 1 minus cosine squared theta is sine squared theta. So that would be one way of doing it. But that you're not as familiar with. If you see it, it's the fastest way to do it by far. But a lot of you aren't going to see it. So what this is, what you're going to see first, potentially, if you're going through that checklist, is you're going to see this this Pythagorean identity. Secant squared theta minus 1 is tangent squared theta. So we get tangent squared theta over secant squared theta is equal to sine squared theta. So this is a Pythagorean identity. And then we could convert everything into sine and cosine. So we have sine squared over cosine squared. And then we have 1 over cosine squared. Okay. And we can multiply both the top and the bottom by the reciprocal of the bottom. So what we get is sine squared theta. This is the idea of dividing fractions, dividing rational expressions. You multiply by the reciprocal of the second fraction. And here you can see the cosine squared theta cancels. Now you have to go all the way down to the bottom where the left side equals the right side. You can't stop here and say they're equal and just stop. Because otherwise, so some people say, well, it's obvious in this one that the cosine squared cancels. So why can't we just say it here? And the reason why you can't just say it here is there would never be a place to draw the line. Why is it obvious here, but it's not obvious here? Or obvious in this step? How do we know it's obvious in this step? Again, it's all about communication, and it's about drawing the line. The line is left side equals right side, and it's obvious. It looks exactly the same. So these sides are equal, but they don't look the same. You need it to look the same. Okay? Let's take another one. Let's take one that's a little different. Let's say that we have secant of x plus tangent of x is equal to cosine of x over 1 minus sine x. Okay, so this one is a little bit harder. That's why I like it. So this is a place where we don't see any Pythagorean identities. This is a good place where we might convert everything into sine and cosine. Okay, now the right side, sorry, I'm used to working at the board where my left is your right. Okay, the right side here, okay, that is already in terms of sine and cosine. So it kind of makes sense to work with the left side. If you notice, I tend to favor the left. It's just coincidence that the left in each of these cases just happens to be the side that that makes more sense, okay, to start with. So this is a good place where you would convert everything to sine and cosine. Part of it is that the right side is all in terms of sine and cosine, okay? In that very first one that we did, that wasn't the case, which is why we left the cosecant of x as the cosecant of x. So this is 1 over cosine x plus sine x over cosine x. And that's equal to cosine x over 1 minus sine x. We're just carrying it down. Then what does that give us? Well, we can combine. Okay, this is a great example because it is a lot more complicated, okay? Reason why it's more complicated is you get to this point and you're kind of like, okay, what in the world do I do? Because they don't look the same, okay? When you see this 1 plus sine x, okay, and this 1 minus sine x, that could be a clue to you. And this is what we meant by squaring a binomial or trying to create a monomial, okay? I didn't want to confuse you by the way that it was written, but this is a good example where you try and get to a Pythagorean identity. And one of the ways that you can do that is you can multiply this 1 plus sine x by 1 minus sine x. Because if we multiply by 1 minus sine x, we get a Pythagorean identity, okay? But what we do on top, we have to do to the bottom. And what this does is, well, this has a 1 minus sine x in the denominator. So we're trying to say, how do we get a 1 minus sine x in the denominator? Let's put it in the denominator, okay? We're saying, we're looking at the other side and we're saying, how can we make it look the same? Well, this has a 1 minus sine x. Let's make it look the same. Let's put a 1 minus sine x here. But if we put a 1 minus sine x in the bottom, we have to do it in the top. And you'll see what happens. And some of you might recognize it from the top more than from the bottom. You know, recognize to do that. So now what does this do? This gets a 1 minus sine x in the denominator on the left so that it looks like the right, okay? So it's going to look like this. On top, we have a difference of squares. Don't leave it as a difference of squares, multiply it. In other words, don't leave it factored. So we got 1 minus sine squared x here. In the bottom, leave it factored. Well, now we can go forward, okay? Because 1 minus sine squared x is a Pythagorean identity. So there's a 1 minus sine x in the denominator on the right. So we put it on the left. You can only work with one side at a time, but that doesn't mean that you can't look at the other side to see what you might be able to do, okay? So the Pythagorean identity turns this into cosine squared x over cosine x times 1 minus sine x. And look what happens. One of the cosine x's cancels. You have to write that last step where the left side is equal to the right. Okay. Now, there is nothing that says that you couldn't multiply both sides by 1 plus sine x. So when you got to this, you could have said it instead, well, there's no 1 plus sine x in the numerator. Let's put a 1 plus sine x in the numerator on the right instead and worked with the right instead of the left. And the same thing would have happened. If we multiplied both the top and the bottom by 1 plus sine x, the only thing that would have changed is that you would have wound up with 1 plus sine x over cosine x on this side, okay? You would have been making the right look like the left instead of the left look like the right. So there are always multiple ways of doing things. Okay, let's do a couple more and then we'll stop. Let's do tangent x. I don't think I did this one. Okay, let's do tangent x plus cotangent x is equal to secant x cosecant x. Let me just make sure that we didn't do this when we were simplifying. No, okay. Sorry, I just wanted to check that I wasn't essentially redoing a problem that we already did. Okay, so this is a good case. Always start with the more complicated side. That can be more helpful. And I would look at this and I would say, hey, I don't see what to do. Let's go to converting things to sine and cosine. So we can convert tangent to sine over cosine and cotangent to cosine over sine. Okay, and this is an example of, hey, we have fractions. Let's combine the fractions. So we're going to multiply one side by sine x over sine x. And as you do this, you can kind of see that things are going to work out for you because you're starting to see squared trig functions. And squared trig functions is going to tell you that you are going to wind up with a Pythagorean identity. You will wind up with a Pythagorean identity with these plus signs because you have to get rid of them. If you look at the other side, they disappear. So you should wind up with a plus with Pythagorean identities. That's the way to get rid of them. Okay. And what you wind up with is we'll do this in 2 steps. Sine squared x over sine x cosine x plus cosine squared x over sine x cosine x, which gives us sine squared x plus cosine squared x over sine x cosine x. Notice in all of these, we're just carrying down the left side. You should write it each time, okay? I sometimes leave it for the very end so that I don't lose track of what I'm doing, but you should write it every time so that you're seeing that the right side just gets carried down. Sine squared x plus cosine squared x is just 1. And you can choose at this point to switch sides, or you can separate this 1 over sine x and 1 over cosine x. I'm going to switch sides. And this is a place where you can jump straight to this step. That would be okay. I would discourage it though. And the reason why I would discourage it is because you want to be clear that you are understanding which is 1 over cosine and which is 1 over sine. Okay, so that's why you can go straight from here to here. That's fine. But I probably actually wouldn't skip over this step. Okay, just so that it's clear that you understand which is sine and which is cosine. Okay, so from here to here, we combined fractions. So put everything in terms of sine and cosine. Then we combined our fractions. We had a Pythagorean identity. And then we substituted our reciprocal functions. We'll do one last one. And I'm doing these, we're getting through them pretty quickly. I wouldn't expect it to take you that quickly to figure out how to simplify without doing a lot of practice, okay? It does take practice. And if you want extra problems, I'm happy to give you extra problems, okay? Very happy to do that. Let's do tangent squared theta plus 1 times cosine squared theta minus 1 is equal to negative tangent squared theta. Okay. So tangent squared and a 1 and a cosine squared and a 1. These have got to be Pythagorean identities. So let's go take a look. Our Pythagorean identities, the one with tangent squared and 1 is tangent squared theta plus 1 is equal to secant squared theta. So we're going to replace this with secant squared theta. Okay, tangent squared theta plus 1 equals secant squared theta. Now, our other trig identity, the one with sines and cosines, is sine squared theta is equal to 1 minus cosine squared theta. So cosine squared theta minus 1 is equal to negative sine squared theta. We switched what was on each side of the minus sign. So because we switched what was on each side of the minus sign, this turns into a negative. Okay. So now we can turn the secant squared into a 1 over cosine squared. Again, we're just carrying down the negative tangent squared. This turns into negative sine squared theta over cosine squared theta. And at this point, you could simplify either side. You can either turn tangent squared into sine over cosine, or you could say this is negative tangent squared theta. Okay, and that would be it there. Okay, so I'm going to stop there. We've done 6 examples. It's not, I mean, you should be practicing more. Please look at the review sheet. There are more examples on there, so please use that to practice. It really takes practice, okay? Because it's just figuring out how can you rearrange things so that they become simpler, okay? And that is it for verifying identities.